So now we're going to talk about the electrical and the mechanical events that occur during a single cardiac cycle. And then we're going to talk about successive cardiac cycles. Now, as I said earlier, the cardiac cycle is essentially one heartbeat. And now what we just talked about, were all of the electrical events of the cardiac cycle that's captured by the electrocardiogram. And in this slide, what you can see is that the electrocardiogram is laid out at the very top of the slide. So this chart that we're going to go through is a common tool that's used to teach about the both the mechanical, which means the physical events that are happening in the heart, and the electrical events that are happening in the heart during a cardiac cycle. And as you can see, what we have is the electrocardiogram is at the top, and then on the bottom, okay, or the rest of the slide, we have different lines to represent different things. We have the purple line, which is representing the pressure in the aorta, the red line, which represents the pressure in the left ventricle, the green line is the pressure in the left atria, the blue line is the volume of blood in the left ventricle, and the light blue line at the very bottom represents the occurrence of heart sounds. So what we're looking at, and what is also happening is all of these measures, okay, and changes in these measures are synchronized in time. So whatever is happening in the electrocardiogram, there is something happening at the same time in terms of aortic pressure, left ventricular pressure, left atrial pressure, left ventricular volume, and the heart sound. So everything is synchronized in time. And as you can see, we also have time divvied up into these different segments, okay? Into these different segments and different phases. And then at the very top, we have the largest sort of division of time, which includes ventricular systole, or contraction of the ventricles, and ventricular diastole, or the resting phase of the ventricles. Okay. So we're going to walk through this one step at a time and talk about each of these different events. Okay. There is a version of this chart in the Sherwood textbook that has a lot of numbers attached to these different events. I've simply have covered it up so that what we're looking at is a little less busy and we don't get distracted by all of these different labels. Okay. And we're going to talk about we're going to talk about the cardiac cycle step by step. Okay. And what basically, one thing to keep in mind is that basically what we're looking at are all of the events of the cardiac cycle as experienced by the left side of the heart, because we're only looking at the left ventricular pressure, left atrial pressure, left ventricular volume, and the aortic pressure. Right? So this is all from the perspective of the left side of the heart. But keep in mind that all of this is happening on the right side of the heart. It's just happening at a lower range of pressure. So the pressures that we're looking at here range from 0 to 120. Okay? In the right side of the heart, if we were looking at right atrial pressure, right ventricular pressure, and then pulmonary artery pressure, what we would be looking at is the same events, but on a much smaller scale, maybe 0 to 20 or 30 or 40. Okay, so step one. Let's cover everything up except for what we're looking at. So the first event that starts a cardiac cycle is the firing of the SA node. Okay? So that SA node fires an action potential, okay? And the first representation of that is the P wave in the electrocardiogram, because the SA node fires and it causes depolarization of both atria. Okay? And that triggers a P wave. So that's the first event of the cardiac cycle. Let's look at what's going on before and then during that P wave. Okay. So first of all, aortic pressure. Okay, the pressure in the aorta is sitting up here at around 80 millimeters of mercury. Okay. So that's one thing. And then all the way down here, we have left atrial pressure and left ventricular pressure, the green line and the red line. So if you look at the period of time before the SA node fires, what we see is that the green line is sitting above the red line. The left atrial pressure is higher than the left ventricular pressure. This is before any electrical activity is happening. Which means if you go over here to this first drawing of the heart, atrial pressure is greater than ventricular pressure. And because that's true, okay, blood is moving in from these veins, both the pulmonary veins and the systemic veins, and blood is moving into the atria and then into the ventricles. Okay? And these AV valves are open. So this stage of ventricular filling we call passive filling, because we're filling the ventricles with blood without needing to contract any muscle. Okay? This is happening in between cardiac cycles. So this is actually happening throughout diastole. So if we look down here at ventricular volume, what we see is that it's increasing. Okay? It's increasing. And that's because the heart is filling. So then the P wave strikes, okay? So then the P wave happens, it depolarizes the atria, and then once it depolarizes the atria, it's going to cause atrial contraction. So over here, down here, we see the contraction of the atria, which is going to push more blood into the ventricles. So if we look over here at the green line and the red line, we can see that the atria have contracted because the green line, which is atrial pressure, has increased. Right? It has this bump up. Okay? And we see that causes a movement of blood into the ventricles, because down here in ventricular volume, that blue line bumps up. Okay? So we get a little bolus, a little kick of blood into the ventricles as a result of atrial contraction. So now, going back up to the electrocardiogram, now we're in the PR interval. Right? This is the time in between the firing of a P wave and the QRS interval. And this, if you recall, was equal to the AV nodal delay. So let's look at what happens once the QRS complex fires. So you get the QRS complex happens once that AV node fires and it passes the action potential onto the bundles of His and the Purkinje system, okay, and it causes the depolarization of the ventricles. Right? The QRS complex is the depolarization of the ventricles. Depolarizing the ventricles quickly leads to contraction of the ventricles. Okay? Now, once these ventricles begin to contract, okay, once these ventricles begin to contract, what you notice down here, looking at the red and green lines, the red line, as soon as you get about midway through the QRS complex and the ventricles begin to contract, that red line goes above the green line. Okay? And there's an arrow pointing at that point. Right here, that arrow is pointing at the point where the red line, ventricular pressure, exceeds atrial pressure, the green line. And over here in the heart, what that means is the pressure down here in the ventricles is higher than the pressure in the atria. When that happens, those AV valves shut. Okay? And they both shut at the same time. Now, when those AV valves shut, if we jump down here, we see that there's a first heart sound. Okay? The closure of both AV valves, right, as soon as those ventricles begin to contract, leads to it causes that first heart sound. The other indication on this graph that we have the closure of the AV valves is that the ventricular volume that was slowly increasing all of a sudden flatlines. Okay? Because there's no more movement of blood into the ventricles, there's no more increase in ventricular volume. It stays the same. Okay? And the volume that is in the ventricles at the end of diastole, the beginning of ventricular contraction, we call that volume end diastolic volume. This is a very important volume. Okay? This represents the extent of filling, ventricular filling. Okay? So now what's happening? We have ventricular contraction, right? We've gotten into ventricular systole. And as the ventricles contract, the pressure in the ventricles are increasing. Okay? And you see this red line, ventricular pressure is increasing. Now, the purpose of ventricular contraction is to pump blood into the arteries, to pump blood into the pulmonary artery, into the aorta. However, in order to open that aortic valve, the left ventricle has to build up enough pressure to exceed the pressure in the aorta. Okay? So the pressure in the aorta is up here. It's that purple line. Okay? The red line is the pressure in the ventricle. So the pressure in the ventricle has to go from way down here, close to 0. It has to get at least up to 80 and above in order to open up that aortic valve, in order to get blood into that aorta. Now, this brief period of time that it takes the ventricle to build up that pressure, that period of time is called isovolumetric contraction. Okay? And if we break down that word, isovolumetric, it is, iso means same, and volumetric obviously means volume. So isovolumetric contraction is a contraction against a constant volume. Okay? And so the ventricle is contracting, the volume of blood is what's constant. Because as you can see, all of the valves are closed during isovolumetric contraction. The AV valves are closed and the arterial valves are closed. So isovolumetric contraction is a period of time where the ventricle is building up enough pressure to open up the aortic valve. Okay? And all the valves are closed during this time. Now, what happens once the ventricles build up enough pressure to exceed the resting pressure in the aorta? Well, the aortic valve opens, and that's what this arrow is pointing to right here. The aortic valve opens. You can see that over here on the picture. And then blood rushes out of the ventricle. And we enter what we call the ejection phase. We're ejecting blood out of the ventricle. And down here, if we look at the ventricular volume, you see it is falling rapidly. So once we exceed the resting pressure in the aorta, we are ejecting all the blood that was in, we're ejecting blood that's coming from the left ventricle into the aorta. And as the blood enters the aorta, it actually expands the aortic wall. Okay? The aorta is getting this very rapid and large bolus of blood. It expands that artery wall, and it causes aortic pressure to rise as well. But if you notice the red line throughout that ejection phase, the red line is above that purple line. Okay? The pressure in the ventricle is higher than the pressure in the aorta. But notice that the pressure in the aorta, the purple line, at its peak is approximately 120 millimeters of mercury. Maybe it's slightly less. Okay? Now, the resting pressure in the aorta was 80. So the aortic pressure is varying from a resting pressure of 80 to a peak pressure of about 120 during ejection. So if you've ever taken a blood pressure, we take blood pressures, and the average blood pressure, are very common. It's somewhere around 120 over 80 in a healthy adult. So this is exactly where it's coming from. The diastolic arterial blood pressure of 80 represents the resting pressure in the arterial system, and the aorta is the origin of the arterial system. And 120 represents the peak systolic pressure, the pressure during ventricular systole that's actually caused by ventricular ejection. Okay. So down here, ventricular volume has plummeted, right? Ventricular volume falls because all that blood is going from the ventricle into the aorta. Okay. Eventually, this ejection phase is going to end. All right? The ejection phase is going to end. It's going to end when the ventricles stop contracting, when systole ends. Now, the volume at the end of systole, end systolic volume, okay, represents the relative empty phase of the ventricles. So if we compare that to the relative full phase of the ventricle at the end of diastole, okay, we had end diastolic volume, and then during the ejection, the volume falls to end systolic volume. Now, the mathematical subtraction of end diastolic volume and end systolic volume gives you a measure called stroke volume. Stroke volume is defined as the volume of blood ejected by each ventricle, okay, during a cardiac cycle. Okay. It is the volume of blood ejected by each ventricle during a cardiac cycle. And it's a very important parameter. It's a very, very important parameter because basically stroke volume is the volume of blood given to all of systemic circulation with each cardiac cycle. Okay? And at that point, stroke volume then enters the circulatory system and is sent to perfuse. It's used to perfuse all of our organs. Okay? And it is equal to the end diastolic volume minus end systolic volume. Okay, so if we look up here at our electrocardiogram, we're in that ST phase. And if you notice, the T phase actually begins before ventricular systole ends. Okay. So portions of our ventricle are actually starting to repolarize, because that's what the T wave is the repolarization of the ventricle. So portions of our ventricle are already repolarizing before the ventricles have finished contracting. And the repolarization tends to happen from the what's called the apex of the heart, or the bottom portion of the heart, and spreads upward, because that's where the depolarization originated, at the apex and moved upward. So towards the end of ventricular systole, the ventricles are already starting to repolarize, and you can see that the contraction is starting to slow down. Okay? It's starting to slow down, and the pressure in the ventricle is starting to decrease. So this next phase, eventually, as that ventricle is relaxing, as that ventricle is relaxing, the ventricular pressure is going to fall below aortic pressure. It's going to fall below that purple line. When ventricular pressure falls below aortic pressure, we have a closure of the aortic valve. That's what this arrow right here is pointing to, is the closure of the aortic valve. And if we look down at the heart sounds, we see that at that point is the second heart sound. Okay? So the second heart sound is caused by the closure of the aortic and pulmonary artery valves. Okay? So ventricular pressure falls below aortic pressure, the aortic valve closes. But the ventricular pressure is still falling. Okay? It's eventually going to go back to its resting pressure, which was near zero. Okay? And it's going to take a little time for it to get there. So the ventricular pressure is falling, okay? And eventually it's going to fall below that green line again, which was the atrial pressure. When the ventricular pressure, the red line, falls below the green line, atrial pressure, only then will those AV valves open up again. Okay? Only then will those AV valves open up again. And when they do, okay, that's what this arrow is pointing to, is the point at which those AV valves open up, because ventricular pressure has fallen below atrial pressure. When it does, you get a rush of blood, passive rush of blood into those ventricles. And you can see in the left ventricular volume this passive rush of blood in. Okay. Now, if we look at this period of time up here where ventricular pressure was below aortic pressure but still above atrial pressure, so the red line was below the purple line but still above the green line, this period of time is another one of those isovolumetric period of time. Okay, if we go back to that, this isovolumetric, instead of it being isovolumetric contraction, really now it's called isovolumetric relaxation. And what's special about this time is that all the valves are closed again. Okay? So, and that's why we call it isovolumetric. So all the valves are closed. The ventricular pressure is falling, and it's falling against a constant pressure. Okay? And the AV valves don't open until ventricular pressure falls below atrial pressure. Okay? Now, what happened to aortic pressure when we closed that aortic valve? What happened to aortic pressure when we closed that aortic valve? We got this little bump here that we call the dicrotic notch. This little bump. And this bump is this reverberation of pressure when that aortic valve closes. Blood reverberates against the walls of the aorta, and it causes this bump in pressure. okay, this dicrotic notch. And what's interesting about this dicrotic notch is that if you directly measure blood pressure in arteries further down the vascular tree, so the femoral artery, for example, which is in the legs, if you directly measure the pressure in that artery, you will actually see a dicrotic notch. Okay? So this reverberation and pressure is actually carried through all the very large arteries. Okay, so this passive filling, if you notice, this passive filling, we don't actually get another P wave until this point here. So you notice that most of the filling of the ventricles is actually being done passively. Okay? Most of the filling of the ventricles during diastole, during that resting phase, is being done passively. And the aorta, excuse me, the atrial contraction that happens at the onset of the P wave is only contributing a small fraction of the total filling of the heart during ventricular diastole. Okay, sometimes this amount of blood is called the aortic kick. It's this last little kick of blood that aortic contraction contributes. Okay. Now the reason why there's so much passive filling of the heart during diastole is because while the ventricles were contracting and those AV valves were closed, okay, the atria, during the entire time that the ventricles were contracting, those atria were still filling with blood from the venous system. Okay? And in fact, ventricular contraction creates an expansion of the volume in those atria that creates a bit of a suction effect. It's called cardiac suction, that draws blood into the atria while the ventricles are contracting. And you can actually see that cardiac suction if we look during the peak of the ejection phase. Okay? If we look down at what's happening in the atria, that green line, you notice that the green line sort of dips down a bit at the peak of the ejection phase. Okay? It represents a bit of a sucking pressure created by ventricular contraction, okay, that draws blood into the atria. So while the ventricles are emptying, those atria are filling. So that as soon as the AV valve opens, there's lots of blood in that atria, and you get this very rapid filling of the ventricles. Okay? And then that atrial kick, the P wave followed by atrial contraction and the atrial kick, triggers another cardiac cycle. Okay? You get a little rise in ventricular volume as a result of atrial pressure, and then the action potential spreads to the AV valve and depolarizes the ventricles again. The ventricles start to contract. You get the closure of those AV valves as ventricular pressure exceeds atrial over here. You get that first heart sound when the AV valves shut. Okay. And then ventricular pressure rises as the ventricular muscle is contracting. Okay. But all the valves stay closed during that isovolumetric contraction until ventricular pressure exceeds aortic pressure and the aortic valve opens. Okay. And then you get, again, this ejection phase, ventricular volume plummets. And eventually, with the onset of the T wave, repolarization and relaxation of the ventricular muscle brings it back down. Okay. So I highly recommend that you work through these slides, this cardiac cycle, and you walk through step by step by step and really spend some time understanding what's going on in the heart at these different phases. Okay. And the quiz, there's a few questions to help you work with this cardiac cycle graph to help you master it.